And finally, to our most important of tools, the periodic table. So the periodic table has been taking shape for over 200 years, and all of the arrangements and everything that we know about it goes back to chemical properties. It wasn't until much later that it was just the electrons and the sublevels and levels that were discovered. In fact, it was about 50 years before the idea of the Bohr model that the elements were put more or less in this arrangement right here. So the modern periodic table, we've got something that looks like this, or you've got the one that we'll be using on the exam. The horizontal rows we call periods, the vertical columns are groups, and we're talking about similar properties, chemical properties and physical properties based upon those similarities in electron arrangement that we've looked at. So some important names for the families that we've seen right here. You've probably seen and heard those before. And a fun tool when you're into chemistry is this website, ptable.com. There's lots of different options. You can check your electron configurations, you can look at orbital diagrams, and you can find out way more properties than you would ever want to know about all of the elements on the periodic table. So you can lose yourself in that for a little while or think, why would I ever do that? And both of those are great. But when we do this, we need to kind of recognize what I just said and what we've seen. The location on the periodic table is connected to the different blocks. So in terms of the AP curriculum, this is stressed a few different times. So what we're seeing is those similarities, whether there's similarities in chemical properties, whether it's similarities maybe in color for some of them, whether it's similarities in density, or any of the other properties that we come up with, it's about the number of levels, the number of electrons in that outermost level, and even more so, the sublevels. So when we're in these different sections, we're talking about filling either the S, P, D, or F block as the outermost levels. The things in the same column have the same number of electrons in that same outer orbital, really focusing on valence electrons. And then any partial filling of sublevels is based upon trends. So if we find something to be true for nitrogen because it's partially full, we would likely see a similar property in phosphorus, arsenic, antimony, and bismuth. So when we find out or know something about our sublevel and how it fills, we can expect other things to be similar. We looked at chromium as an exception to the Aufbau principle because of the 4s1 3d5 that kind of broke our expectations. Well, molybdenum and tungsten, the two elements right below it, have similar differences. And once we get into the D block and then down into the F block, you see that even more. So although we are not expected to know every possible weirdness, we should be expected when presented with something to be able to explain it or to be able to connect to what other elements may have similar properties or may have similar either exceptions or similar trends that are significant. Some of the questions that I've seen on the AP test have come back to just such simple relationships within families on the periodic table that a lot of times people get frustrated when they're asked, well, fluorine does this chemically, blah, blah, blah. And then when asked for an explanation or a similarity, people try to do a lot of great things in terms of bonding, in terms of all of these other ideas, when really the most important thing when understanding how things are similar, when we're thinking about what's similar to fluorine, is realizing that it's going to be chlorine, bromine, and iodine. Those are in the same family.